So I'm a graduate student in Dr. Anderson Janati's research group, and for this work, we collaborated with Dr. Bharat Jalan and his graduate student, Jin Ye, from University of Minnesota. And before I go on, I just want to acknowledge funding from National Science Foundation and computational resources at Exceed. The main motivation for this work were the experimental observations from our collaborators, where they grew thin films of dysprosium scandate on thin films from deuterium titanate on dysprosium scandate. As you can see here, at temperatures around 1400 degrees Celsius, the thin films are fully relaxed and single crystalline. Photo emission of these thin films showed some features around 1 eV, which were attributed to titanium 3D that were the lower Hubbard band of yttrium titanate, a broad peak from oxygen 2p, and an unknown peak around minus 11 eV, which could not be identified. Furthermore, they did resistivity measurements with respect to temperature on these thin films as well as bulk of yttrium titanate, and found an activation energy associated for these two for conductivity. So in our work, we mainly focused on justifying the origin of this broad peak at minus 11 eV and the cause of this emission activation energy for conductivity in yttrium titanate. So in this talk, I will begin by talking a little bit about Mott-Hubbard insulator yttrium titanate, followed by our computational approach. And then I will discuss the structure and electronic properties of yttrium titanate, formation and migration of small hole polarons, and the optical transitions they can participate in. And lastly, a little bit about the dependence of Mott-Hubbard gap on TiO6 octahedral tilting. Yttrium titanate is a prototypical Mott insulator where the gap is dependent on electron-electron interactions. It has been recently applied in complex oxide heterostructures as a barrier for 2D electron gas formation. Shown here is an example of gadolinium titanate being used in strontium titanate as a barrier, such that the 2D electron gas is formed at the interface. And usually, this material is grown by chemical methods, but our collaborators used MBE for this growth on dysprosium scandate and lanthanum aluminate substrates, as shown in this XRD data. Some interesting properties of yttrium titanate arise due to its rare earth origin. The rare earth elements of the periodic table are known to form distorted perovskite structures. And in yttrium titanate, this distortion of TiO6 octahedra can be compared to that of gadolinium ferrite or GFO type. Magnetic moments of these titanium atoms in yttrium titanate are ordered ferromagnetically up below a temperature of 30 Kelvin. Above that, this material is paramagnetic. Even though the calculated band gap of yttrium titanate is around 2 eV, it has been observed repeatedly that optical transitions begin to arise around 0.6 eV. And that is, again, something we will address from our results as to how we can justify this low-energy photoemission, low-energy onset. So in this computational approach, we have used density functional theory with meta-GGA scan and HSE functionals as implemented in VASP. For core and valence electron interaction, we have used PAW potentials with 500 electron volt cutoff. We have turned spin polarization on with ferromagnetic and anti-ferromagnetic orderings into consideration. And lastly, we have used a gamma-centered 6x6x4 K-mesh for structural optimization of primitive cell, but a single K-point calculation for supercell. So the structure of yttrium titanate is shown around here with experimental lattice parameters labeled along these edges. These distortions of TiO6, these tiltings of TiO6 octahedra can be observed both in plane, as shown here, and out of plane along c-axis as shown here. The fully optimized lattice parameters and TiO3 angles obtained from SCAN and HSE are comparable to each other and deviate only slightly from experimental values, which is expected of both these functionals. However, the electronic properties differ greatly between the two functionals. Shown here in the band structure of YTO using meta-GGA scan, we can see that the gap between lower and upper Hubbard band is very small. It's only 0.28 eV, and it cannot be noted in a simple density of states calculation. However, with HSE, the gap is highly pronounced, around 2 eV, 2.03 eV, which is in excellent agreement with previous calculations. And this gap can be clearly seen in the DOS plot. So here I will just mention that the antiferromagnetic ordering in yttrium titanate is not stable, and so we did not go ahead with that configuration. And therefore, now we compared the calculated DOS of YTO with experiment, and we're able to justify most of the features. First one being the lower Hubbard band, which actually in our calculation is quite pronounced, but it does appear at 3 eV above oxygen 2p, as shown here. Also, this broad emission is indeed oxygen 2p, as suggested by the experimentalist. But there is no feature around minus 11 eV, so we could not justify it with this DOS calculation alone. At this stage, we noted that the thin films in this measurement were in fact only 10 nanometers thick, and they were grown on dysprosium scandate, where we have F electrons that could play into this. And so we went ahead and did a DOS calculation of dysprosium scandate and observed a rather significant contribution from dysprosium 4F into the total DOS of DSO around minus 11 eV. These results are justifiable because there are similar reports of XPS measurements exist. And so we aligned this DOS with that of yttrium titanate and compared these aligned DOS with the experiment. And clearly, this broad shoulder does in fact come from the substrate, especially the F states in the substrate. The next thing that we studied was the thermally activated charge carrier transportation. As I mentioned earlier, there is an activation energy associated with bulk yttrium titanate, and other works have also reported similar values of activation energy for bulk of this material. Seebeck coefficient measurements have indicated a p-type conductivity, so naturally our next step was to study the formation and self-trapping of small hole polarons in this material. And so when we did that, we found that the polaron will be formed at titanium sites, and the compression of these titanium-oxygen bond lengths is around 4.4%. The self-trapping energy of this polaron is calculated to be about minus 0.65 eV, which indicates that the polaron would prefer to be in a self-trapped state rather than delocalized in the lower Hubbard band. And next, we studied the migration of this small hole polaron from its origin site A to the nearest neighboring site, site B, via intermediate configurations in which the polaron is delocalized between these two sites. Shown here is the case of 50% distribution between sites A and site B. And so from our calculations of this migration, on the configuration coordinate diagram, we can clearly see a barrier of around 0.27 eV associated with this migration path. And this migration energy is in good agreement with experimentally observed activation energy for polaron hopping. Okay, so as we have seen that the self-trapping and migration energy barriers are quite lower than the band gap, we can use these two processes to justify the optical transitions which are seen at 0.6 eV. And so the process one that can take place in these, with these Polaron is the transition from site A to a state in site B, which would begin at energies lower than this peak energy due to the presence of optical phonon modes. And therefore, we can use process one to justify how the observed optical excitation onset is actually lower than band gap. Another process that can take place with these Polarons is the excitation from the small Polaronic state where it is formed into a delocalized state. Again, this would begin at energies much lower than the peak energy of 1.29 eV. And so in combination, both processes 1 and 2 can be used to justify the observed low optical transition onset. And lastly, I will just mention how the band gap in yttrium titanate depends on TiO6 octahedral tilting. Here's a plot of band gap calculated with HSE versus the TiO-Ti angles in AB plane and along C-axis. And there is a linear decline of band gap indicating a strong electron-electron correlation in this material. Looking at the electronic structure of the two extreme cases, we could say that the lower Hubbard band in the distorted case, where the gap is 2.3 eV, eventually disappears, and we get only a metal in this case when all the distortions have been taken away. And so to conclude, we can have the following few points in the summary, that the broad peak that we saw in photoemission is in fact coming from the substrate, especially the 4F states in the substrate. The holes that are formed in this material prefer to be self-trapped instead of delocalized in the lower Hubbard band. The migration barrier is in good agreement with activation energy that was measured for conductivity in this material. Optical transitions that these small Polarons can participate in can actually be used to justify the low onset of optical excitations in this material. And lastly, the band gap of YTO is highly sensitive to TiO-Ti bond angles, which indicates strong electron-electron correlations. And with that, I can take questions. Oh, yeah.
Can you comment on how that might affect your results? It seems like kind of a small number of electrons.
Oh. You mean here?
Right.
Yeah, I agree. That might affect the results, but so far we have only taken into account this this distribution of electrons in titanium. But yeah, that's something we need to still look into. Yeah.
Thank you for the talk. I have a question about this migration rate, the migration barriers. What kind of calculations do you use to get the energies? I mean,
HSE.
no, but I mean, okay, maybe we can discuss.
Okay. And what type of calculations, DFT?
It's like a technical question.
You mean how I get the diagram?
Yeah.
Oh, okay. Yeah, we calculate the configuration coordinate diagram. There's like a method. Yeah.
Short question. So considering the sensitivity of the band gap with respect to the tilting of the titanium oxygen angle, so how does scan
Probably not, because as we saw, the structure with scan is also similar to the one we obtained with HSE. So at least in that sense, I don't think with scan calculation this is related to.
So meaning that, electron correlation does not influence the structural channel only, but also a purely electronic channel.
Yeah.
Yeah, I had another question. You had the band gap versus the TiO, TI angles. Were you just manually fixing those angles, or how were you changing those angles?
Yeah, I was manually fixing, like systematically decreasing by a few degrees without really distorting the octahedra itself, because if I move a little bit awkwardly, like the 90-degree angle would be disturbed.
Other questions, comments? If not,